In this work, we propose MEGA-DAgger, an imitation learning method for learning from multiple imperfect experts. Existing interactive imitation learning algorithms assume having the access to a single optimal expert, whereas in real-world scenarios, we usually only have access to multiple imperfect experts. For example, in the autonomous racing scenario, we usually can only have multiple experts that cannot provide perfect demonstration at every round. During the learning process, we may want to collect demonstration data from all of them and learn a cumulative policy that takes the advantages on every expert. In order to effectively apply interactive imitation learning in such scenarios, we need to address the challenges of undesired and conflicted demonstrations. Here is a comparison between our proposed MEGA-DAgger and MEGA-DAgger, a well-known interactive learning algorithm. By comparison, the racing policy learned using MEGA-DAgger with 5 imperfect experts can overtake in scenario that policy learned using MEGA-DAgger fails to overtake. The learned policy with MEGA-DAgger can also outperform the expert, as demonstrated by the video on the slide. Because MEGA-DAgger learns a cumulative policy by strategically selecting the goal state action pairs from different experts, it is able to outperform the expert. Here is a MEGA-DAgger algorithm. The algorithm starts with an empty global dataset and a randomly initialized novice policy. It iteratively incorporates demonstrations from each expert into the global dataset and train a new novice policy using the updated dataset. The core part algorithm are the data filter and the conflict resolution function. As seen in the slide, both MEGA-DAgger and MEGA-DAgger incorporate the gating function to allow the expert take over the control and provide demonstration. When comparing to MEGA-DAgger, the improvement that MEGA-DAgger add to the learning loop and training pipeline is mostly the data filter and conflict resolution in order to cope with the incorporation of multiple imperfect experts, as labeled in the orange box on the slide. We will first talk about the data filter. Let's still take autonomous racing as an example. When the vehicle collides with obstacle during the demonstration process, we will want to remove this undesired step, along with some previous steps that bring the vehicle to such undesired state. To mitigate the challenge of undesired demonstrations, we design a data filter that can strategically terminate the rollout and truncate undesired demonstrations. The data filter is based on the control barrier function. The safety score is calculated by the subtraction between the CBF values of 2 consecutive time steps. If the safety score becomes negative, the current rollout will be terminated, and a fixed number of demonstrations will be truncated at the end of the dataset. Before performing the actual evaluation, we first perform some preliminary experiments to find out the most suitable beta, which is the truncation steps for our scenario. So we first change the beta parameter and see how it affects the performance of our method. As the image on the right side of the slide shows, we show how the number of truncated steps, which is beta, affect the performance of the policy in terms of overtake rate and collision rate. For the truncation step, we empirically find that when beta equals to 70, both overtake rate and collision rate works the best. After setting up the parameter, we evaluate the effectiveness of our proposed data filter using lane switchers with different undesired behavior probabilities as expert. The lane switcher is an algorithmic oracle that has access to the transformation and state of both the ego vehicle, the opponent, and the track. So it is able to plan perfect trajectory for the ego vehicle. To incorporate undesired behavior into the analysis, we introduce PU, which is a chance of undesired behavior to happen. When the undesired behavior happens, we reverse the steering angle from the oracle and speed up the vehicle to make it easier to collide. On the right side of the slide, the green bar represents policy with the data filter applied, and the red bar represents policy with random truncation of the same number of steps. We show that using the data filter demonstrates noticeable improvement over random data truncation, both in terms of overtake rate and collision rate. After going through the data filter, let's talk about the second part of the algorithm, which is the conflict resolution function. To resolve conflict, we propose a function for checking similar observations and scoring the action associated with these observations. We first determine similar observations by calculating cosine similarities using matrix manipulation in one batch with respect to similarity threshold. Then, for our context of autonomous racing, we use a linear combination of safety score and equal velocity after min-max scaling normalization as indication of safety and progress respectively to choose a best action and overwrite all other actions with similar observations. As for the cosine similarity threshold, we perform hundreds of rollouts while changing the cosine similarity threshold and find that when setting the cosine similarity to 0.95, it works the best for our scenario. The left side surface plot indicates the connection among the cosine similarity threshold, number of rollouts, and the collision rate, whereas the right side indicates the connection among the cosine similarity threshold, number of rollouts, and the overtake rate. As the red circle in the plot indicate, when cosine similarity is set to 0.95, the policy reached to the peak performance. We should roughly evaluate and compare MEGA-DAgger with HE-DAgger in the context of autonomous racing. When compare MEGA-DAgger, HE-DAgger with the data filter, and HE-DAgger without the data filter on different maps, we show that policy learned using MEGA-DAgger can outperform policy learned using HE-DAgger in terms of both overtake rate and collision avoidance on various different maps consistently. We also evaluate and compare the policies learned using MEGA-DAgger with the expert. As the table and graph indicate, the learned policy is able to outperform all experts by leveraging the complementarity goal demonstrations. As the collision plot visualization indicate, the collision from different experts forms a complementary distribution. By using the data filter and conflict resolution function, we can aggregate goal demonstrations from all experts together and ultimately learn a policy that is able to outperform all imperfect experts. We also deploy the learn policy onto a real vehicle and show that the learn policy is able to safely perform overtaking when racing with an opponent vehicle. The video on the slide shows the policy deployed on the physical vehicle with the opponent being pure pursuit algorithm. And as the video illustrated, the ego vehicle is able to overtake the opponent multiple times effectively and safely. We open source the code to facilitate further research and contribute to the community. The code can be found by scanning the QR code or accessing the hyperlink on the slide. Thank you for listening.